you want to use this one? Okay. All right. We like for the people in Zoom, is the audio working? Do you hear us? Yes. Excellent. Infinitely excellent. Okay. Welcome to the Dev Exchange. Very quick information before we start with the presentations. This event is part of a series of 4 events in the year that are developer-oriented about COMPAS that the COMPAS Association organizes. There is like 3 dev exchanges, which are the smaller, like more informal meeting formats or meetup kind of. And then we have the Dev Day, which happens this year, will happen in May, and it is a bit bigger. And this is the old logo, and the new logo contest is on, so submissions are required. The Dev Day is like a full morning of speakers, demos, well, whatever, and then ápero. And then the Dev Exchange is a short afternoon of the speakers, demos, and ápero. Very quick one today, and I have an incorrect URL. There we go. Wait, I'm not sharing on Zoom, so people in Zoom cannot see this. So we have this now, if you want to brand your project as made with COMPAS, if you're using COMPAS, you can use these badges, like in the Shields IO tradition. It comes in 2 styles. You just link this, and it's an image, and it looks like this, which will be the Antikythera project presented today. You know, these little badges that you can put next to all your other badges. All right. The agenda for today, we will actually switch a bit around. We will start with the presentation of Chen about Antikythera to control all the things. Then we will go to an online presentation by Arnout and Simon, making robotic 3D scanning easy. And then Eric will present COMPAS ThreeJS. And after that, drinks and chips. All right. That's all from my side. Chen, you want to?
So the people on Zoom see this. I'm not in the Zoom meeting. Yeah, we sure. Hi, I'm Chen. With Gamma Secola. And I'll present to you a project Gonzalo and I have been working on since a couple of months. A really cool development. And the background is a lot of different research that's been done in the chair around robotic assembly, human-robot collaboration, the whole idea of building plans. I put this is a criminally inaccurate timeline. some of these things don't even overlap, but visual first, an architect move. But some of the projects I'm referring to as for example, Victor Long's research into special assembly of special timber structures with like a distributed robotic system. Some InnoSwiss projects that a couple of them I was involved with around creating an AR building plan to replace papers that the timber planners produce, and timber people use in the hall to assemble, mostly timber frames. And maybe the most kind of known around here and most recent is COMPAS XR, just kind of like an infrastructure for digital XR-based workflows to enable human robotic collaboration. And after all this, Antikythera comes in. And here we maybe a bit what we ended up doing to as of like a lesson learned from all these projects. We started working on a distributed process manager or orchestrator, which would let us orchestrate fabrication processes. At the heart of Antikythera is the blueprint. Blueprint is a description of a fabrication process in a no-code way, kind of. Right now, baking it are JSON files. In the future, we'll add some kind of nice authoring tool. And this blueprint is resolved into a directed acyclic graph, which describes the sequence of tasks to be executed. And our orchestrator then assigns these tasks to agents, which can be anything. It could be a robotic control agent, it can be a smartphone, it can be a human. The session is the blueprint as it's executing, and it follows the status of the blueprint. And the orchestrator exchanges messages with the agents to let them know when and what and with what context they should perform their actions. And they respond back with the status, success, failure, and some output. Prepared a live demo, God help me, to try and kind of illustrate, maybe this was a bit abstract. I'll try to do it with one hand. So hopefully you can see on the top left is our Antikythera dashboard. And you can see here I've already uploaded some blueprints, which can be viewed. Yeah, a bit too small, apologies. But essentially, there's a start and an end, and anything in between are tasks that are defined in the blueprint. And the other three windows are agents, which I faked using Copilot. Agent 1, Agent 2, and Agent 3 are the ones that will be executing these tasks. And they're not going to do anything. They're going to sleep and for some time. And then they'll finish, succeed or fail. I'm going to start now a new session, meaning from the blueprint, I'm going to start a session. And now this is a very kind of hello world example. It's a task 1, agent 1, task 2, agent 2, task 3, agent 3. And you can see that the Antikythera follows their execution status, and when all of them have finished, the session is complete. If I ask one of them to fail, hopefully the execution will fail once I start it. So now agent 1 is running, and agent 2 will fail, after which I'll be able to resume. This is all very kind of fake, but hopefully you understand, you kind of realize that these agents can be, for example, robotic planning or robotic execution, or maybe even an instruction to human to assemble something. So now you can see it failed. The session is failed. If I now recover the agent, so the failure of the agent signifies, I don't know, planning, robotic planning that failed, or don't know, RC timed out and the controller stopped answering and the agent crashed, whatever. So you can see the session. It's very hard without a mouse. The session is now in a failed state, but it's not dead. I can recover the agent, or it recovers itself. So now I flipped it here to succeed. And once I resume, agent 1 is already finished per the blueprint. So the execution starts again from agent 2 and moves to agent 3, after which the session is complete. Of course, the agents can share data. Let's see if I prepared another fake agent that lets me make a choice, just to illustrate that agents can and do receive data during execution, and that data is propagated through the execution, meaning agents or tasks can rely on data produced by other tasks. And here you can see I chose Morris and Tenon, and agent 2 is now milling a Morris and Tenon. Well, one of them, or both. Of course, if all we could do is sequential execution, this would be a bit useless. So here, I can go back to my trusty agent 1. Here we have a parallel execution, meaning agents or tasks 2 and 3 are gonna start at the same time. They might not finish at the same time, but once both of them are finished, the blueprint is successful. Cool. Another essential piece of another essential kind of feature, which is approaching real-world scenarios, is we have the ability to compose blueprints. So in this example, I've composed the same Hello World blueprint of the 3 tasks, but it's now composed within both of these. Sorry, I can step in. It's probably just extremely small, but I can step into them and take a look, and you can see it's the same tasks. And once I start a new session, now the entire cycle is gonna execute once per each of these composite tasks. So this is one cycle complete, and now the next cycle begins. And the last part of the demo and very real world, so real world that we've used it recently, and I'll show in the end, are dynamically expanded composite tasks. So these are, here we have the same blueprint, and it executes for each element of a model, for example. So Antikythera has first-class support for COMPAS model, which means that it has sequencers that are usually project-specific, but we've written some very basic ones. And so here you can see this is a top-level blueprint, and it has this X1, which is a single task. But once I start a session and I select a model, so these are models that I've uploaded into Antikythera before. Names are pretty much meaningless. But you see now this single task has expanded, given a very stupid logic that we have in a very stupid sequencer. But now there's a composite task for each element in this model. And then I can run this. And now each agent is each iteration of these three agents is operating on a single element. So this was one element, and now comes the next element. Unfortunately, you can just see the GUIDs, but yeah, in the future we'll be able to see a bit more. Like we faked a really nice screenshot of a model shown in the data store. So the data store shows real-time data that's being shared across the tasks, like the model ID, and this will one day show some visual stuff using Eric's excellent 3JS based COMPAS viewer. I'm going to stop this because this will run forever, and this is all I wanted to show for the demo. Just really quickly, so what's actually happening behind the scene is we have we have basic protocol. The orchestrator. The distributed part of this is there's no peer-to-peer communication. Everything talks over some MQTT bus, and we've created a basic protocol. Where the orchestrator, when the time is ripe, assigns a task, given the requirements in the blueprint, and then the relevant agents, which are listening on the same bus, they can claim the task. Once they claim it, the orchestrator allocates it. This might seem a bit complex, but there's actually different execution modes. Some of them enable, for example, multiple agents to execute the same task in a competitive way. Maybe they can all complete it. Maybe once one of them completes it, the rest should stop. So all of these messages are to accommodate that. Once an agent completes a task, it sends a task completion message back to the orchestrator, and eventually the orchestrator answer with an acknowledgement, which in some execution modes may tell or indicate, because we can't tell the agents anything, to the other agents to stop what they're doing. So maybe a few things that weren't super visible in the demo, but are critical features of Antikythera. It's platform and location independent. So this is accommodated thanks to the MQTT bus and this protocol I presented. The session is persistent. So there's a database backing up and saving the status of the execution of this directed acyclic graph live. So the session can be paused. I mean, we're planning here for fabrication processes that may last anything between a few hours and a few days, weeks, or maybe months. And they should, right now we're faking it a bit, but ideally we shouldn't have to kind of restart always, right? The session should express what's up with your fabrication process. Right? So this goes back to the building plan concept. And so the session is persistent and it can be paused and resumed. If it fails, it can be reset and started again from where it failed. It's a less code fabrication process. So once the agents are implemented and you've created your blueprint, you shouldn't have to write any code. Especially if you already have a fabrication process defined, but you just want to modify, change the order, change the sequence of things. You'll be able to do that without any coding. I mentioned the sequencer, the very simple one we made, but we acknowledge that sequencing is a project-specific kind of task. So we have like a pluggable interface for defining sequencers. And as I mentioned, COMPAS in general, specifically COMPAS model, COMPAS Timber are first-class citizens, meaning you can upload a model, you'll be able to view a model, and the execution of the blueprint can follow the logic of a model. This is a bit this is a developer exchange, and this is the stack we've used. The Copilot was used heavily. There was no appropriate. No, I just forgot it there. We used TypeScript and React Flow for the front end. We used Python, of course, and Fast API and ImoDB as our database. That's all in the front end, in the back end, sorry. And in between and all around, we have MQTT, of course, using COMPAS Eve, I believe, right? Yeah, using COMPAS Eve, I forgot. We have COMPAS Timber, we have COMPAS Model, we have COMPAS Protobuf for the communication and data exchange. What's coming next? I'll be done in a second. Yeah, some kind of a graphical authoring tool for the blueprints. Right now, it's a bit of a nightmare to edit these JSON, unless you ask Copilot to do it. But it's a hit or miss. It's getting better. Some kind of an agent catalog that's relevant, of course, to AC. That way, some processes are going to be literally no code. So we can see how some robotic execution agents based on RC, robotic planning based on COMPAS Fab. These can be fairly generic and offered. And some more elaborate flow control, retry policies. Behavior trees is something that we've flirted with in the past and we might revive. It increasingly seems to make sense. That's it. This is a bit heavy, so maybe I'll just show. So Antikythera already had like a first real world test or validation, whatever, and we've used it for our Timber demonstrator downstairs. So here you may or may not see Antikythera orchestrating the robots. So it does the planning, does the robotic execution. It triggers to some extent the CNC machine. And when it's all done, it waits nicely for us to put in the screws and be done with it. Thank you. You can ask questions if you have any. Or she's here, so. Questions? Yeah. You're talking about the sequencers. I repeat the question, if we can infer a sequence from the hierarchy in the model. Yeah. 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 This part is, we kind of acknowledge, is completely project dependent, and yeah, and so this sequencer that I showed, it's 4 beam in model beams make a task, right? So the order they are in, but it can be arbitrarily complex, and it can take into account the hierarchy of the. Basically, the pluggable is you write some code. It's a sequencer. You get the model, and you spit out tasks in whatever way your project requires, right? So it can take into account anything COMPAS Timber, anything COMPAS model, can take into account the hierarchy, can take into account the interaction graph. Right now, it's a stupid iteration, and yeah. But this part is, it was tempting to try and and do something, but it's hard to do something meaningful, detached from a project. I skipped the blueprints of this demo, but here we had a double nested blueprint because we had a stock material, which was a long piece of timber that had to be put in the CNC, and then it was cut by the CNC and milled, and it was no longer this long stock. Now it's individual beams. So we had to do like for each stock, for each element in stock. So that's what the sequencer looked like for this particular project. The granularity of the model was per slab, so it's like per slab, per stock, per element. Do this, yeah. Philip? No, sorry. The agent. Okay. Agents are any process that speaks this protocol. And then agents have tools, and the tools are anything from a simple Python function to they can call arbitrarily complex code. So an agent could look like, so for example, for this demonstrator, we had an RRC agent, which had a pick and place tool. So, and then the tasks correspond to tools. So you had a task pick and place element, and then it called a pick and place tool with all the required context for the tool to know now. So as I mentioned, model is first class, so the tools have access to the model and they have access to the context, meaning they know which element they're operating on. They know what to do to the element based on the implementation of the tool. They know what to do it on based on the context of execution. So this is context provided by the orchestrator to the tools based on like a pre-processing step, which is the sequencing. So sequencing is a pre-processing operation on the blueprint, which turns the blueprint into a blueprint session. So remember wow, this doesn't work. the single X1 task that then expanded into many of these X1 tasks, each one for. Was that your question? Did that answer? Yeah. Okay. Robot. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Yeah. Yeah, there's a lot of abstraction in between, right? With all this protocol and MQTT. Tasks are basically one-to-one paired at runtime to tools. So task, tool. And tool is a piece of code. We have two workshops. We have a workshop upcoming. So we're gonna have a workshop in the future of construction. It'll be like a COMPAS Timber plus Antikythera plus CAD work. We're gonna show something cool. Yeah. Maybe another workshop. Don't know yet. Cool. Thank you.
Thank you. Okay, before we jump to the next presentation, which is going to be remote, I wanted to mention Anna is here. The Future of Timber conference, is it conference, right? It's going to happen in September 17th and 18th at Bloomer Lemon. What else should I say? If you have questions, ask Anna here. And this one, cool. Perfect, thank you. Okay, now we will go to Arnout and Simon. Let's see if we can coordinate this somehow. I guess I need to unplug and we switch, yeah.
Hi. Shall we take it from here, Gonzalo, or is that what we do?
Hear you yet.
Can you hear us?
Yes.
Okay, great. Arnout, you will share the presentation, right?
Yes, I will. All right.
Okay.
Yeah, and can everyone see me? See the presentation?
It's, yeah.
There it is.
Yeah.
Nice. All right. Hello, everyone. My name is Simon Griffioen. I am a teacher and researcher at the University of Applied Sciences in Amsterdam. And within this university, we also have this what's called the Robot Lab, where we do where we research digital fabrication. And I'm presenting, we're presenting today with Arnout. So Arnout will actually present his work, what he did with us as an intern. So Arnout is a third-year ICT student who did an internship of 5 months with us. And I will just quickly give a short context before Arnout will take over. Because I think it was very nice, this call from Gonzalo. It was very, it was like I would say like a very low barrier call to join this presentation. So I think that was very nice, and I also learned that Gonzalo helped Arnout a bit during his internship with some technical challenges. So I thought, okay, hey, let's at least answer this call with showing what Arnout has been working on. So it's not so much, let's say, a COMPAS development contribution, but more, I think, an appreciation for how COMPAS can be a nice bridge between let's say, a student with no background with Grasshopper robotics or Rhino Grasshopper design, but still can be this nice tool set for students like Arnout, who's coming from an ICT background, and to really start developing right away, making tools within this very short time frame. So I think that's very cool. And I also thought it was nice to just send the signal from Amsterdam that we're slowly also adopting COMPAS more and more in our lab here, and not so much because I'm forcing it on my colleagues, but really because it's solving issues that we're all facing when we try to develop things within this environment. All right, so then a couple of slides. Yeah, exactly. So the Robot Lab, we're positioned, we're trying to integrate practice, research, and education all within the lab. So that means that we really would like to combine education and research as much as possible together with practice as well. So we really try to involve students in the research we're doing. Research that we're doing always is in collaboration with practice. And this is really how we try to work within the small team that we have. If you go to the next one, Arnout. And this is also very important for us that we really focus on empowering students within the lab. So we really give students access to the facilities in the lab as quick as possible to have them help develop things. Also because we're at the applied university, the focus there is very much on learning by doing. So every student is very used to hands-on work. Meaning that also the challenges that we give are always based on making prototypes and working with the tools as fast as possible. Next one, yes. Then we're also a very multidisciplinary team. One sec, Arnout, before you go to the next one.
Yeah, you went too far.
But no, it's okay. Very multidisciplinary team. So we're a group of architects, but also mechanical engineers, product designers. Also this photo is not representative anymore of the team we're also changing a bit, but you can also see at the top Marta Alemani. So she's the one who, let's say, initiated this lab here within Amsterdam. If you go to the next one, so how we like to work is always to we do our research always focused on research questions coming from practice. So we always want to do this really from an industry partnership perspective. And then I think there's just 2 more slides. Yeah, exactly. So we are positioned within Amsterdam, which also has this ambition to reduce to also be fully circular by 2015 and to reduce 50% use of raw material, which also poses, I think, a nice environment for the Robot Lab to really focus on these challenges. So we're also very much focused on construction for that reason. And one of these directions that we recently have been taking, if you go to the next one, Arnout, is also really focusing on how technology can help upskill wood upcycling. And we have a couple projects that revolve around this, and one that is sort of the initiator of what Arnout was doing is Branch Out, where we look how we can use leftover irregular wood into construction. And this is also then where robotic scanning comes into place. If you go to the last one, exactly. So here for this research project, we developed this robotic setup. Can you play the video, or is it? So here we developed this robotic setup where we have a Zivet camera mounted on the robot on the mill motor, and you have an external rotary positioner, and that let's say positions any irregular object so that we can scan it from multiple angles and then combine it into a, let's say, unified point cloud. And the goal here was that we would like to work with these setups more and more, but we also noticed that running such a setup is kind of complex, and as I said earlier, we really want to empower students and involve them in doing these kind of works. So that was then the challenge given to Arnout also from, okay, how can we take such a setup and how can we make this more accessible for students to play around with and also use this technology in their own projects, in their own courses, or in their own graduation projects. And that's then what we challenge Arnout with.
All right, yeah, so as Simon introduced, this was my internship project, basically making robotic scanning more accessible to students. Now, who am I? I am Arnout Roodenberg, as Simon introduced me, as a third-year software engineering student, now former intern at the Robot Lab and a very passionate rower. Now, the goal of this plugin, as was already introduced, is to make it easier for students to use robotic scanning, because we do get a lot of students who don't know how to code, basically. And if you have to, our previous setup was just fully a proof of concept in a full repository, and to teach a student to download an IDE, how it works, how to set it up. And if you then have to scan a bunch, this was not really accessible to them, so to say. So that is where I came in, and that is how I was challenged. Now, firstly, since this is of course a COMPAS conference, how did I use COMPAS? Now, my entire plugin is developed in Python using the COMPAS componentizer. So that was very useful, because otherwise my entire plugin wouldn't have been possible. Furthermore, I have used COMPAS Eve components pretty extensively throughout my development, as normally perpetual functions aren't possible in Grasshopper. Grasshopper just freezes up. But with the COMPAS Eve multi-threading, this made it very possible, so very useful to me. Now, my plugin is divided into 3 different sections: scanning, auto alignment, and utilities. Well, scanning speaks for itself, more or less. Auto alignment is more just about giving the scans its digital location, so they appear in our 3D models, basically where they would have been in the robotic setup. And utilities are things that didn't fit neatly into one of the other categories, but weren't enough components of them to make their own categories. Now, scanning. As I go by each section, you can see in each section header which components I've developed for that section. So in this case, there are 3 of them, but 2 we'll be discussing. In this case, manual scan, which is a simple scan component that makes it possible to just make scan. It does allow single scans, but because it only allows single scans, it does not need to communicate with the robot itself. So it's not hardware or location specific. And in theory, anybody who has, in this case, a Zivid scanner, because that was the hardware setup it was developed for, can use these components out of the box. Furthermore, we have an MQTT scanning component. This is meant as more of a workhorse scanning component, where you can just load up a robotic program and it will do it automatically by itself. That does unfortunately mean it is set up specifically, as it relies on MQTT. For example, the robot communicates with the PLC communicates with the broker communicates with your laptop, and your laptop communicates with the scanner. Now then, the auto alignment process, for which you can see the needed components here. As I said before, this component is basically this part is basically composed mostly of components that are used in giving the scans that we make in the scanning process their locations. This happens by using the scanning positions or robot planes, robot positions you want to scan from, turning them into a 4x4 matrix as basically a step to just make it accessible to multiple other Python functions, instead of purely using Grasshopper specific coordinates. And this matrix is then fed into other components. Now, once you have the matrix, it is as simple as combining it with the scan through the transformation component, and you get a scan with a location. I do want to add that this seems to be not purely Grasshopper specific, so any program you load the scans into will continue to have these locations. Now, furthermore, just some utilities, mainly calibration and also config, which I will talk a bit more about later or now. Config is basically what provides the structure the plugin expects. So you give it a file path and a prefix, and it will file path to an empty directory, and it will, in that empty directory, generate a file structure for you, which the entire plugin expects, and basically puts in all their outputs and gets in all their inputs. So this is where your scans go. This is where you get them. This is where all your specific settings files go. This is where they're gotten. And then calibration, because same as with manual scan, this plugin makes calibration both easy and possible from any location, because it once again only needs the camera. Well, furthermore, it doesn't really need to be connected to the camera even then. And this and calibration basically works by the robot taking a bunch of scans and taking a bunch of positions you took the scan from, and then checking exactly where it is related to the positions you've given, because those positions are often tool center points and not precisely where the camera is at that moment. And it takes this, so it takes the positions, it takes the scans, and it makes a transformation matrix, which is practically an offset to the TCP. Now here, a demo of how it works. So basically, we start with a config component. We put some planes into the role positions. We start up MQTT with a background component running, confirm it works. And then you can start your robot program, and it just starts scanning for you. And here, once the scans are taken, you can transform them, give them locations, and then just import them. Now, during this demonstration, I want to add something went wrong. We used the wrong settings files to take the scans, which you can also then, it's a good takeaway to be very careful, because settings can produce wildly different results. For example, this was a data set we made using the same settings file, and the results, as you can see, vary wildly. And here now, as for use cases, this was a project of a student I was working with for his graduation project, and his project basically involved making an automation script for an automatic repair system using the robot, and also entirely within Grasshopper. And what was cool to see was also that he used my plugin at certain points to make his scans and turn them into meshes, which he could then further use to model his repairs. Now, lastly, some takeaways from someone that started this internship completely outside of the Grasshopper ecosystem. No experience with robotics, some experience with CAD programs, but not years, not significant ones. And here are some takeaways that I got. Basically, the way, because Grasshopper works very interestingly with its own environments, and which makes them very fragile. Because normally, when I'm working with the usual IDEs, I can just import whatever I want. In Grasshopper, that is not the case, because as soon as it needs to modify a file that is in use, it corrupts. So it was a very interesting learning process working through all that, and also seeing the possibilities of Grasshopper as a program. So it was a very interesting perspective for me to gain as a just purely IT student who's only worked with programs specifically for coding. And I would furthermore like to thank all the COMPAS teams, because I got a lot of good inspiration from looking at the open source repositories of how those plugins are built and how they are structured. And this was very helpful to me structuring my own plugin. And yeah, that is the end. Are there any questions?
Okay, thank you very much. It was very cool. All right. Question in the chat? No,
Chat.
there are no questions in the chat, I think.
I will look at the chat then, because, all right. Yeah. Question in the chat.
I don't see any.
I don't see any questions.
I actually have a question. It's sort of an open question too, but I think I speak from personal experience and probably a few others in the room who got their taste of coding starting with Grasshopper. And so I sort of feel like when I code, I think in a sort of Grasshopper way, almost as by default. And then, so I wonder if you have any other insights coming from, let's say, the other side, is discovering it with already having a lot of experience with coding.
Well, yeah, basically, the code mostly functions the same, of course. So that is nice, but there are a lot of little things. For example, you can't pass dicts in Grasshopper. Like I just said, you can't update, you can't import certain things, and you have to work around a lot more things, which I had to really adjust to keep those things constantly in mind. For example, otherwise, a very specific thing is that if you take the inputs of a component in the code and in the metadata, those names have to match. Because normally when you call a function, you can give different variable names as variables, which led to a lot of, oh, right, that doesn't match because like one typo or whatever. So Grasshopper is really strict on you. Plus, since everything runs single-threaded, everything had to be the whole plugin had to be a lot more divided, because otherwise you would cause quite long freezes whenever functions automatically triggered. So to keep it snappy, some components had to be divided up in multiple.
Thank you.
Does that answer your question?
All right, thank you very much. If there are no more questions, then I think we will switch to Eric.
I'm gonna try to do some magic. Bit of a setup here to do, but green. Oh, then it's. I don't. Okay, but
the screen?
yes, because I can extend it, but it doesn't. I cannot. Yes, but I want to duplicate it, and it.
Resolution. Duplicate. I don't know if it has. If you can change what's the resolution that you have now on the second screen. Change this one. Yeah. To I don't know. Try full HD for now. Convert things 20 times.
Yeah. Oh, cool. Okay. So, hi, my name's Eric. I'm a researcher at Grammatikular Research. I'm an architect and computational designer. I'm going to present a small project that I was working the last weeks. It's COMPAS ThreeJS. Is based, or it works also thanks to COMPAS protobuf and to COMPAS protobuf TypeScript library that I wrote. Oh, yeah, okay. That we wrote together with Chen. So, hello world. And I want to bring you like, somehow like a bit like a narrative where I see the 3D space as the universe. So I will start by Act 1, so it's the abstract. Nothing's happening, but what we are doing is importing this new COMPAS ThreeJS library, and especially the viewer. So we can define our universe, and I decide to call it viz. So yeah, oh, typo. And the universe, of course, needs to be started. It needs a big bang. So we call viz start, we save it, and we run it. And we see that in our localhost, there is this universe. It's void, nothing happening, but I do know somehow that I am in the mid of this universe. So I can start to add geometries to this universe, and I want to start with something very simple, let's say a point, and I want it at the center. But I need to tell my universe that this point is part, so I just say add geometries, and then I give this variable. For the moment, it's not that important. And a point appears at the center. It's nothing very fancy, but quantum mechanics suggests that if we change our point of view and we just take these points and we change just one little name, and let's make a bit fancy, we can give some other values, let's say prime numbers. And this we call it movement, and we add to viz the movement. Then we do have a vector. Wow, 3 weeks of work for a point and a vector. Yeah. We're getting there, we're getting somewhere. But I want chaos, the universe is made of chaos, so I can ask some more mathematical stuff, and I tell them to be part of my universe. And then we restart it, and and then I have some points around. They are not fully chaotic, but I do not really understand the pattern. It's called a strange function. I don't fully understand, but I can also ask it to make order of these points. And so we relaunch it, and then finally have some more patterns emerging from all these points. Now let's jump to the Act 2, the physical. So we do restart from our points, they are just doubled, but all these things are abstract. I want some more matter. So let's create a mesh from this strange point cloud. And then I can add it directly to my universe, but I do need something else. I need to be material, because it's not abstract a mesh. So I can create a material. And I say that my material has color blue. And then I can tell that my material has a roughness, it has a metalness. And then finally I can add my mesh to my universe with a specific material. And then I do rerun it. And yeah, but it's black. Okay, we're getting there. So we have the matter, but we still need lights. So let's add some light. First we had a point light. I can say it's color white. I want in this position, and the helper is just a little geometry, abstract geometry, that will help me to identify where it is. So we can add it, launch it, and nothing happening because I didn't save the file. Oh yeah, of course. I still have to add it to my universe. And finally, we have a small little sun. Okay. There is also other two types of light that we can add, rectangular light and spotlight. And yeah, I'm happy with that scene. Okay, let's jump to the new act, Act 3. So in the Act 3, there is an evolution. There is a new actor, and this actor will say that the sphere is a lie. Wow. Okay, of course, we just created a bunch of points and then we connected them and then there was a sphere, but it might also not be a sphere. And my new actor is saying that some strange morph, new geometries, I don't really fully understand. But what my new actor is doing an action. So I can define a new action. Let's call it metamorphosis, metamorphosis, and we give it a value, a generic value. We don't really care for the moment. And then there is this small, powerful poem that it's not really important what it is doing. It's more about this new actor, that it changes this geometry, this mesh, and also some colors apparently, but then we can just update it, both the geometry and the material, and then we can rerun it. But nothing is still happening because we still haven't defined the actor. And the new actor is called slider. So we can define the actor slider. We have an action called metamorphosis, and then we just label it, and we add it to our universe. We relaunch everything, and finally our actor is appearing up here. And then as our actor does it, our geometries start morphing into new geometries, back and forth, and what else? And our actor decides that he kind of like this donut-shaped geometry. So, Act 4, the eternal return. So, in our Act 4, we start with our yellow donut. It's very simple. And talking about actors, I can still take this donut, move it around, and rotating and scaling and what else. And I can also ask to give me informations. So for the moment, it has a frame, this thing with radius and other information that we don't really care at the moment. But we're talking about time and the eternal loop. So we want our universe to mix the end at the beginning and other things. And we do it with another action, another method, and we call it animate. And it's function on time. And since we move on time, we can start creating transformation of this geometry. So we can take this torus and we can apply a small transformation, and then another transformation, and another transformation, and change other stuff. And then we can just update the geometry and update the material. We can later say, as the universe becomes a big giant loop, that the loop of our universe is called animate. And as we run the Act 4, we have a donut spinning around crazy. So my demo is finished, but I'm happy to answer questions or showing you some other examples. Thank you. So for animation sliders, it's a live update. Python works as a backend and TypeScript, the web as a front end. So there is all these messages going back and forth to this WebSocket, and in this case, my TypeScript calls, send a message to my Python, animate, changes the torus, and then it sends back the new updated information on how this geometry should be. But every time I modify my Python file, I have to rerun everything. Mhm. It is what is happening. No. Yes. Yeah. Um, I think technically yes, but it's still not implemented. But yeah, I think because it's just a WebSocket, and I think it's possible to create a new one and just send new information. Yeah. Okay. Yeah. 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 Mhm. Yeah. I think in the chair we have some ideas. We have an idea to use it for as a visualizator for the compass timber model. We're gonna have a project that might benefit from it. Also, other Antikythera wants to use it. I know the acoustics team also has some interest. So the long-term goal could be a lot of thing. If you have suggestion and you're interested in using it, you are more than welcome to join and participate. I think this is just the basis, but we can build a lot on that. We also want to start visualizing and simulate robots. Mhm. Mhm. Yeah. Um, Hen is asking if in the COMPAS ThreeJS side there is already all the primitives of the geometry that we need to work with COMPAS. At the moment, yes. I mean, all primitives are there. It has helpers to visualize points, vectors, frames, planes, and all or more abstract geometries. Meshes are fully supported. Volumetric meshes, I think it's possible if they are transformed to normal meshes before. Yeah. Yeah. Yeah.
The sliders, for example, the moment that you interact on the front end,
Yep.
it sends back the data,
Yep.
does something, sends back the
Yep.
updated geometry. For the looping, this update happens, is triggered from the front end or from the back end? For example, the interval, how fast this thing rotates.
Yeah. So 3GS works in a loop. So to do animation in 3GS or the simplest version of animation, it's already a loops. Like exactly you define a function and it just creates a buffer. How it here is implemented is every No, here every time so this loop stays in the threeJS side. What the server behind the viewer is doing is creating its own loop. We can also change the interval of this thing, and then it's calling this function inside while this loop. So these two loops are separated and just continuously send information. Yeah.
Running online or local?
They are running. So the viewer takes the geometries, and with Compass protobuf, he creates a stream of bytes. They are sent through this WebSocket, and then the front-end side, the TypeScript, decode all these bytes and then creates the geometry.
And there's another one from Lee.
So it's local. No, it's everything runs local on the computer. Yeah.
Thanks. And there's one from Lee. Really great presentation. Question: any plans to also support BREP, I assume, NURBS?
Yes, I've been working a little bit with that. It's a bit a hot topic at the moment. I managed to visualize BREPs with using Compass OCC. The only way to do it at the moment is having a BREP, transforming to a mesh with Compass OCC to view mesh, and then send it to the viewer. Yeah.
Yeah, you can't really visualize a BREP directly.
Okay. Yeah. Okay.
You will have a lot of triangles and a lot of data. If you pre-compute this into a buffer geometry, then especially with the protobuf interface, probably you can send this very efficiently. But you have to pre-compute and then pre-compile into the buffer geometry. But can I ask, sorry, about this loop, because it's not entirely clear actually. Are you running that loop definition in threeJS, or you're just running a similar loop in threeJS?
It's just a similar loop. So this loop stays in the backend.
So this loop is one iteration of your loop, and then there is a fixed interval for running that. Okay.
Yep. I can maybe find it.
Right, so this is the ticker of your loop, basically, the animate. It's like one.
Yep.
Okay.
So here's my class viewer, and then if I look for, no, it's sorry, it's in the viewer, but it's actually in the server. And no, maybe
is it not a run until complete?
No,
oh, no, this is the infinite loop.
Maybe.
But it's okay. I just wanted to understand what how the definition of the compass function related to the.
And then it must be. Yeah, it's here. So I have this while true loop, counter that is just the time that I put. Then it sleeps for a loop interval that it's defined. The default is 001 seconds. And then if I do have a callback, I call this function every X seconds and just sends new data.
Yeah, but so it doesn't need to send the data every single time?
No.
Yeah, thanks.
I guess for things that do not change, you can also just send the transformation directly to the threeJS instead of sending the updated mesh.
It's also not really deleting a mesh and recreating a new one. Is
moving the vertices.
No, applying the transformation to the new mesh. So there is the old
the
object.
Python applies the transformation of the threeJS.
This is the threeJS applying. This one? No. Oh, yeah. Yep. Yep.
The Torah is already there.
Yep. No, it sends the new object fully, but it will just get the transformation or the new endpoints, and then you just take the old objects and transform it. No, no.
But this now works like that because you have a primitive on the other side. But if you do this for a mesh,
No, it also works with a mesh.
here you would not work.
No, it still works.
Yeah?
Yeah. I don't have an example showing it, but it works.
It works on this machine.
Anyway, this whole project is more than the loop. It has a lot of more nice things than just looping.
No, there are some very software engineering choices, very discussable, both in Python and COMPAS ThreeJS, but
metadata that you display when you select the object.
Yeah.
Can you, let's say can I define which properties do I display, or you just take whatever?
So at the moment, because I didn't want to spend too much time on that, it just takes the data property of the COMPAS thing and it just displays it as it is. But I think it with custom attributes, everything can be displayed. Yeah.
Thank you.
Thank you.
Now we're going to go for a beer and chips. Thank you, everyone.